Hello students, welcome to today's lecture on compiler design. Today we will discuss about the LALR parser, uh, which is an extension of CLR parser. So we know that CLR parser and LALR parser are the most powerful parsers and also the advanced parsers compared to simple LR parser. And among all the LR parsers, CLR parser is the most powerful one. And you can view this LALR parser as an extension of CLR parser. So let us begin the LALR parser, how we perform the construction of parse statement. First, you need to understand what is LALR. LALR stands for look ahead LR parser, whereas in CLR, C stands for canonical look ahead LR parser. Here also, just like in CLR parser, in LALR parsing also, we use a canonical collection of LR of 1 items. So we use the same thing. Canonical collection of LR of 1 items will be used to build the LALR of 1 parse table. Okay. So after finishing the LALR parser design, you will understand that it is similar to CLR parser except one simple step. So that step will be added over here. These are the steps, the same steps used in CLR parser also, starting with checking the ambiguity of the grammar. And if at all any ambiguity is there, eliminate the ambiguity of the grammar. Then add an argument production to the given grammar and find the canonical collection of LR of 1 items. So till this point, it is same as a CLR parser. And here comes one more step here after calculating canonical collection of LR of 1 items. What we do is we will identify the sets, the states with the same set of productions but with different look ahead symbols. Okay, so here after calculating the canonical collection of LR of 1 items, what we do is we will identify the states which contains the same set of productions but with different look ahead symbols, and then we merge them into a single state. That is the only additional step required, except that everything else is going to be same as CLR parser. That means if you understand that CLR parser design, you understand the LALR parser also, because the steps are going to be same. Okay, so after merging the states, again you draw the data flow diagram and all construct a LALR parsing table by using the same process which we used in CLR parse table. Okay, so let us have a look at all these steps one by one. A small recap here. What is LR of 1 item? LR of 1 item is nothing but LR of 0 item plus an additional look ahead. Okay, so we saw this in simple LR parser, LR of 0 items, and with an additional look ahead, we form LR of 1 item. Okay, the look ahead symbol always starts with the dollar for the argument production, and then we continue the process for by calculating the LR of 1 items for the remaining production. So the argument production should always begin with the look ahead symbol dollar. You need to remember this point. Okay, right. Let us understand this with an example. I am considering the same grammar which we used for constructing CLR parser. S implies capital A, capital A, capital A implies small a, capital E implies small b. So if you remember, the first step is checking the ambiguity of the grammar. It can be easily verified that this grammar does not contain any ambiguity. So step 1 is completed. Okay, and then step 2 is adding an argument production and inserting a dot as first symbol of every production, and also adding a look ahead symbol dollar for the argument production. So the argument production is simply S dash implies the original start variable S, and put a dot at the first position of every production, and the argument production will have a look ahead symbol dollar at the beginning. Okay, so this step is same when compared with CLR parser. It is same as CLR parser only, so there is nothing new here. Now calculating canonical collection of LR of 1 items. So we'll begin with I0 state. I0 state is calculating the closure of the argument production. That is closure of argument production is S dash implies dot S comma dollar. Okay. So how do you calculate this closure of any production? By looking at the symbol after dot. What is the symbol after dot? It is a variable. If it is a variable, what we do is we add all the productions of that variable into this statement. Okay. So we add the productions of capital S, that is dot AA, comma, and calculating this dollar is again going to be first of beta this dollar, that is first of epsilon dollar. I explained this calculation of look ahead symbol of new production, generated production in LALR Parser. Just go through that video again to understand how it is calculated. It is like this: we add the production of this S, that is S implies dot AA, comma, look ahead symbol is calculated like this. The variable or terminal, that is after that dot S, what is the symbol over here? It is epsilon. We have nothing here, therefore it is epsilon. So first of epsilon dollar is going to be dollar. Okay, first of epsilon dollar is going to be dollar. So that is how it can. S implies dot AA, comma dollar. Again, we need to perform the same operation, that is calculating the closure of this production now. Because we have a variable after dot, we need to add the productions of capital A. So what are the productions of capital A? Capital A has two productions. Capital A implies small a, capital A implies small b. So we add these two productions, and calculation of these look ahead symbols is like this. How to calculate is first of capital A dollar. First of capital A dollar. So how do you calculate first of capital A in original grammar? First of capital A is the terminal, the first terminal that begins the RHS of the production, that is small a and also small b. So the first terminal is small a and small b. Therefore, first of capital A is small a, small b. So we add that small a or small b as look ahead symbols here. And for this also, because uh, for capital A, it is going to be same set of look ahead symbols. Okay, so because these two productions are generated from this production, we use the same concept, first of capital A dollar as look ahead symbol for both the productions. That is nothing but AR. Okay, so and now these are the new productions generated, and if you look at the symbol after dot, they are terminals. Therefore, no new productions will be added over here. So now I naught contains four productions. S dash implies dot S comma dollar, S implies dot AA comma dollar, A implies dot AA comma ARB, A implies dot B comma ARB. So this is also, the process is same. If you remember, this process is same as LALR parser. There is nothing new added till now, and we continue the process uh, of calculating all the LR of one items. So this is I naught, and for every symbol after dot uh, for each production, we produce a new transition on that symbol. Okay, so here the first production has capital S after dot, so a new transition will be added on capital S. This contains capital A after dot, so a new transition will be added on capital A. The symbol is small a after dot, so a new transition is added on small a. Here it is small b, so a new transition is added on small b. So what happens with this is just move the dot a step forward. Okay, so now it becomes S dot. This dot is move forward. So S dash implies S dot. While moving forward, the same look ahead symbol will be copied. So it is dollar. Okay, right. Because we don't have any symbol after dot, state is completed. So it will not produce any new productions. And here it is moving dot after A produces S dash implies A dot A comma dollar. While moving that dot forward, the same look ahead symbol will be copied. So dollar is copied. Now if you see, after that we have capital A. Now because it is a variable, the productions of capital A will be added here. Okay. Now you need to calculate the look ahead symbols. See, calculation of look ahead symbols is first of epsilon dollar here. First of epsilon dollar is dollar. Again for this also it is going to be dollar. Okay. And on this again you have capital A after dot. So ARB will be added directly because we are just moving dot forward. Okay, and because we have a variable capital A, productions of capital A will be added, and calculation of look ahead is like this: first of epsilon ARB, that is ARB only. So we get ARB in both the productions. Okay, and on small b, just move forward b dot, and the same look ahead symbols will be copied while forwarding the dot. So A implies B dot ARB, right? Because we don't have any symbol of dot, it stops. Similarly, we calculate I5, I6, I7, I8, and I9. Okay. Now, if you look at this diagram, the actual LALR process begins now. So up to this point, it is same as CLR parser. You can refer to that video, CLR parser design, to understand how it is actually designed. So this is what we get. These are all collection of canonical LR of one items. Now the LALR step is, the additional step is, identify the states in which the same set of productions are available, but they may be look ahead symbols different. So if you look this uh, I3 and I6, look at this I3 state and I6 state. See, the productions are same. A implies A dot A implies A dot A implies dot A implies dot A implies dot B, A implies dot B. So LR of 0 items are same. That means the productions are same, but the difference is in look ahead symbols. Here it is ARB and here it is DAL. So what we do is we merge these two states into a single state and rename it as let us say some I36, and merge the look ahead symbols. Okay, so what we get is I36 will be a new state, and A implies A dot A, comma A or B or dollar. So we merge all the look ahead symbols into a single set. Okay, so I3 and I6 will be merged together by combining the look ahead symbols in each production. Okay, right. So similarly, if you look at uh, this I4 and I7, see, I4 and I7 is also having same set of LR of 0 items, but with look ahead symbols different. So you can merge these two, I4 and I7. Similarly, if you look at this I8 and I9, these two can be merged. Okay, so now after merging, what you get is this new DFA. Okay, so I3, I6 is merged together, I4 and I6, I7 are merged together, I8 and I9 are merged together. Okay, and the connections will be uh, remaining same. Okay, right. So this is the DFA of LALR parser. Now, once you get this new DFA, you can construct the LALR parser table by using the same rules which we used in CLR parser. That is, if any state is having a transition on terminals, it corresponds to a shift operation. And if any state is having a transition on variables, it corresponds to the go to entry. And if any state contains a end of dot, that is if you do not have any symbol after dot, then it corresponds to reduce operation. Okay, so you need to identify the same set. So here the productions are not written. If you write the productions here, then you will get the idea about what are the reduce operations. Also, if you look at the previous diagram, the reduce operations are this one. I4 I7 becomes reduce operation because we have nothing after this dot, and I1 also uh, represent accept operation, and this I9 I8 also represent reduce operation, and I5 represents reduce operation. Okay, so any production or any state, if it contains productions with nothing after dot, will contribute to the reduce operation, reduction operation. Okay, so fill up this parser table by using the same set of rules we used in CLR parser. For example, I will explain how to fill that shift operation. For shift operation, you need to look for the terminals, transitions on terminals. So this is I naught with small a is going to I36. Therefore, I naught on small a is shift 36. You need to fill like this. I naught on small a corresponds to shift 36. Okay, or you can use a single state. You can rename it as a single name. 36 is a name of the state. Remember that it's not two symbols. 36 is the name of single state. Please remember that. Okay, and I naught on B, I naught on small b is moving to I47. Therefore, it corresponds to a shift operation 47. Shift 47. I naught on B corresponds to shift 47. Okay, so that is how you can fill up this entire table by using the same set of rules we used in CLR past table. Okay, so before you fill this LALR pass table, please listen to that CLR pass table video again, then come back to this, then fill this pass table. Okay, and how to utilize this pass table is explained here. If the entry corresponds to a shift operation, it means that if anything has shift yes something like this, then it means shift the corresponding input symbol along with the state. Okay, shift the input symbol and the state onto the stack. That is the meaning of shift operation. And reduce operation means that remove twice the number of mod beta items from the stack. Okay, and then add the symbols onto the stack. Then the symbols to be added is, the first symbol is the LHS of the handle with which you are replacing. So that is the first symbol. And then find this goto of SM minus R comma A to fill the last symbol. So this process is same as SLR and CLR. We have gone through this process. So in any LR parser, the process of using the parse table is going to be same. There will be no difference. So for SLR or CLR or LALR, using the LR parse table is going to be same. There is no difference at all. Okay. So we'll make use of the same process to perform that shift and reduce operations. Okay, so if the action represents accept operation, then the parsing is completed by accepting the input string and therefore halt the process. Otherwise, if any action corresponds to an empty cell, then it means there is some error in the input. The input string given is not part of the corresponding grammar. Therefore, they invoke any error recovery routine and perform the corresponding error handling operations. Okay. And here is the task for you to utilize the pass table and process the string small abb. So abb belongs to that corresponding grammar. Therefore, after processing, you should end up with accepting the string. Okay, so what you need to do is use that topmost symbol of the stack and the input symbol. The combination is, let us say I am explaining the first step you are going to do. The combination is 0 comma a. So look into the pass table. What is 0 comma a is saying? It is saying shift 36. So you need to perform, the action is S36. That means shift a into this stack and also 36 into the stack. Assume 36 as a single symbol. Okay, and continue the same process, right? So on 36, the next symbol will be there. So continue the process and perform this processing operation. Uh, at the end of the processing, that means when you reach dollar, you should get this action, accept action. Okay. Then only the process you performed, the steps you followed is correct, right? So that's all with this LALR parser. What you need to understand is LALR parser is same as CLR parser, except that after calculating the canonical collection of LR of 1 items, you will be identifying the states in which the productions are same but maybe the look ahead symbols are different. So identify such states and merge them into a single state. There may be more than two states also in some cases. In this example, we identified only two states for merging, but sometimes you may have, let us say, I3, I6, maybe some I10 will be there with the same set of productions with different look ahead symbols. Then merge all of them into a single state. Okay, so that is what you need to understand. That is the only difference between CLR parser and LALR parser, except that everything else is going to be same. So that is why LALR parser can be viewed as a CLR parser with LR of 0 items plus the look ahead symbols merged together. Okay, so that is what LALR parser is. So if you understood that CLR parser, you can definitely understand this LALR parser very easily. So practice that CLR parser because it is the most important topic from this unit. Okay, so that's all for this class. With this, we have finished the design of LR parsers also. In our next class, we will discuss about how to perform this error recovery operations in LR parser. Okay, so because if you see, if the action is corresponding to some error cell, that is empty cell in LR parse table, then we are saying that there is some error recovery routine that will be invoked. So what are the different possible error handling mechanisms, error recovery strategies? We will discuss about them in our next class. Okay, thank you all. When we come back, we'll discuss about error recovery strategies in LR parsers. Thank you.